When an engine fails on a multi-engine aircraft, there will be a decrease in thrust, and on propeller-driven aircraft, an increase in drag on the side with the failed engine. The results will be that the airspeed will decay, the nose will drop, but most significantly, the aircraft will yaw immediately towards the failed or dead engine. Controlling that yaw is of vital importance. The yawing moment is the product of thrust from the operating engine multiplied by the distance between the thrust line and the centre of gravity, the thrust arm, plus any drag from the failed engine multiplied by the distance between the engine centreline and the CG. The strength of the yawing moment will depend on three factors: how much thrust the engine is developing, depending on throttle setting and density altitude, the distance between the thrust line and the CG, the thrust arm, and the drag from the failed engine. If rudder is applied to counter the yaw, it will generate a moment which is the product of the rudder force multiplied by the distance between the rudder centre of pressure and the CG. At this initial stage, the pilot's ability to counteract the asymmetric yawing moment will depend on the rudder displacement, which affects the rudder force, the IAS, also affecting the rudder force, and the CG position, affecting the rudder arm. Under a certain combination of conditions, control difficulties can arise under asymmetric thrust. Let us assume that the live engine is at a high thrust setting, the rudder is at its full deflection, and the CG is at its rearmost limit, that is, giving the shortest rudder arm. If the IAS, the dynamic pressure, is just sufficient to produce enough rudder moment to counter the yawing moment, there will be no yaw. However, any decrease in the IAS will reduce the rudder force, and the aircraft will yaw uncontrollably towards the dead engine. This uncontrollable yaw, in this case to the left, will cause the aircraft to roll uncontrollably, also to the left, owing to the greater lift on the starboard wing whilst yawing left. The aircraft will enter a spiral dive to the left, which at the low speed would be impossible to stop with flight controls alone. If this were to happen close to the ground, the result would be disastrous. In these extreme circumstances, the only way to regain control would be to minimize thrust on the live engine or engines, to remove the yawing moment and permit a controlled forced landing. Thus, there is a minimum IAS at which directional control can be maintained under a given set of conditions after engine failure in a multi-engine aircraft. This minimum speed, which will vary with temperature and density, is called VMC, minimum control speed. There are different speeds for ground and air engine failures, and for different configurations. These are described fully in due course. One of the factors influencing the yawing moment following engine failure in a multi-engine aircraft is the length of the thrust arm. That is, the distance from the CG to the thrust line of the operating engine. In the case of a prop-driven aircraft, the length of the thrust arm is determined by the asymmetric blade effect of the propeller. At positive angles of attack, the thrust line of a propeller rotating clockwise when viewed from the rear is displaced to the right. This is because the downgoing blade generates more thrust than the upgoing blade. This phenomenon is fully explained in the lesson on propellers. If both propellers rotate clockwise, the right or starboard engine's thrust arm will be longer than that of the port engine. So, if the left engine fails, the thrust of the right engine acts through a longer thrust arm and generates a bigger yawing moment, and a higher IAS would be necessary to maintain directional control than if the right engine failed. Thus, at a given IAS, the given situation would be more critical if the left engine failed. The critical engine, then, is the one that would give rise to the biggest yawing moment if it were to fail. To overcome the disadvantage of having a critical engine on smaller twins, their propellers may be geared to rotate in opposite directions, or counter-rotate, with the downgoing blades inboard, giving both engines the shortest possible thrust arm. Bigger turboprop aircraft, such as the King Air and larger, will have co-rotating propellers, turning in the same direction. In the case of four-engine jets, either outboard will be a critical engine. Although the moments are balanced in the diagram on screen, the forces are not. The unbalanced side force from the rudder can be balanced in two ways, either with the wings level or by banking towards the live engine, which in a marginal situation is the preferred method, as will be explained shortly. In the wings level method, rudder is used to prevent yaw, and the ailerons are used to keep the wings level. Yawing towards the live engine gives a side-slip force on the keel surfaces behind the CG opposite to the rudder. The turn indicator will be neutral, and the ball central. This paradox of asymmetric thrust, where the aircraft is side-slipping but the ball is in the middle, is the exception to the rule of balanced coordinated flight. The advantage of the wings level method of balancing the forces is the strong horizontal visual and instrument reference available to the pilot. The disadvantages are that extra parasite drag from the side slip will reduce climb performance, which would be vital when close to the ground, and that there is a possibility of fin stall if the side slip angle is excessive, which would worsen directional control problems considerably. It is more aerodynamically efficient to balance the rudder side force by banking towards the live engine, so that lift gives a lateral component to oppose the rudder force. The bank angle must be restricted to 5 degrees to prevent significant reduction of the vertical lift component. Banking towards the live engine also reduces the side force on the fin from side slip, which effectively reduces the yawing moment and gives more rudder authority to stop the yaw. The cockpit indications on the turn coordinator will be no turn, but the ball will be out to the right. This is the corollary of the indication in the wings level method, there being no side slip, but the ball is not central. The advantage of this method is its better aerodynamic efficiency, without the side slip drag penalty, making it better for use in marginal situations. But it is more difficult than the wings level method for the pilot to fly consistently. In practice, however, pilots will tend to use the wings level method initially, with its simpler handling references, usually combining the techniques only under marginal conditions, when the better aerodynamic efficiency of bank to the live engine or engines is of greater importance.